All right, in the next part of the section 4.3 material, we're going to talk about some applications of separable differential equations. And the examples that we'll look at in the second part of this section are pretty classic examples that you would see in any Calculus 2 course or introductory differential equation course. So this first type of problem that we're going to consider is what's called a tank problem, or sometimes called a mixing problem. And here's our setup. We have some tank, which is containing initially 120 liters of pure water, and we have a mixture containing 100 grams per liter of salt, which is entering the tank at a rate of 2 liters per minute, and then the well-mixed solution inside of this tank is leaving at the same rate at which we're pouring this solution into it. So for this example, we might be interested in determining, well, what is the amount of salt in the tank at any given point in time? And we can answer that question by modeling this process with a differential equation. So what we're given in the problem statement is information about how quickly the amount of salt in the tank is changing based off solution that we're pouring into the tank and solution that is leaving the tank at these given rates. So what we're interested in this problem is the amount of salt in the tank at any given time. And in part A, we're asked for an initial value problem which describes this process. So let's start by introducing some notation. We're going to let y of t be the mass of salt. In this example, I'm going to measure mass in grams in our tank after a period of t, which is going to be non-negative since we're talking about time, minutes. So what I'm interested in is this quantity y, and I'm given in the problem information about the rate at which y is changing. So in particular, the rate at which y changes, that is the derivative of y, can be described by the following equation. We have salt, which is coming into the tank at a given rate, which would be an increase in the value of y. So I'm going to have a positive rate at which salt is coming in. And then we have salt leaving the tank at a given rate, which will be a decrease in the amount of salt in the tank. So a negative value for the derivative for the rate at which salt is leaving the tank. So in general, the rate of change for our salt content will be the rate at which salt is coming into the tank minus the rate at which salt is leaving our tank. So let's see if we can find these rates of change. So we know in the problem statement that salt is coming into this tank at a rate of 2 liters per minute. So we will have 2 liters of this solution being poured into our tank each minute. And within each of these liters, we have 100 grams of salt per liter. So we've got 2 liters coming in per minute. We're going to multiply by the mass of salt in each one of those liters. Now, we're told then that this well-mixed solution is leaving the tank at the same rate. So for our rate out, we have solution leaving at the same rate of 2 liters per minute. And now let's think about how much salt is in each of these liters which is leaving my tank. So within the tank, we were letting y denote the mass of salt in grams. So at any given time, I have y grams of salt in my tank, and this solution, we were told, is kept well mixed. So this y grams of salt will be divided equally among the 120 liters of liquid in this tank. So 120 liters comes from the fact that initially our tank had 120 liters of water, and the rate at which we're pouring solution in is the same as the rate at which solution is leaving our tank. So we've got a constant volume of 120 liters. So from here we can simplify a little bit, and we have dy dt is equal to 200 minus 2y over 120, or y over 60 grams per minute. So we have this differential equation for the rate at which our salt content is changing over time within this tank. So this is our differential equation describing this process. And we're asked in this question to find an initial value problem for this process. Now recall, an initial value problem is a differential equation together with some initial condition. Now we already have our differential equation, and the initial condition comes from this statement that the tank initially contains 120 liters of pure water. That is, the mass of salt at time 0, at the moment that this process starts, is going to be 0 grams. Now, why 0 grams? Well, we were told that this is pure water initially. There's no salt in this. Hence, we have 0 grams of salt at the moment this process starts. So this condition is our initial condition. And so these two things together, my differential equation and my initial condition, form my initial value problem. Now, once we have this initial value problem describing the rate of change of salt in our tank, we can try to solve this equation. So in the next part of our problem, we are asked to solve the initial value problem that we found in part A to determine the amount of salt in the tank after t minutes. So what we found in part A was the differential equation dy dt is equal to 200 minus y over 60 with an initial condition y of 0 is equal to 0. Now this is an example of a separable differential equation. We know how to solve this using the material that we saw in the early part of section 4.3. We can separate our variables and integrate. Now, one thing I might do in this example before separating my variables is I might simplify my equation a little bit on this right-hand side by factoring out a constant 1 over 60. So if I factor out a 1 over 60 from this right-hand side, I would be left with 200 times 60, or 12,000, minus y, with the same initial condition y of 0 equals 0. So if I want to solve this differential equation, I could make use of separation of variables. If I were to put everything with the variable y on my left-hand side, I would have dy over 12,000 minus y is equal to 1 over 60 dt. So once I've separated my variables y and t, I can now integrate on both sides. And on the left-hand side, I'll have the negative natural log of absolute value 12,000 minus y. Now this negative out in front of the logarithm is coming from the fact that we have a negative in front of our y value. What we're really doing here is making a u substitution with u equals to 12,000 minus y, so that du is negative dy. So this negative that we have in front of the dy gives us the negative in front of that logarithm term. And on the right-hand side, the antiderivative of 1 over 60 dt is t over 60. And then we've got some constant of integration. So from here, I'd like to try to solve for y explicitly, if possible. And there's a few ways that we could go about doing this. One way that I might proceed to start with is by multiplying both sides by a negative 1. So I would have the natural log of 12,000 minus y is equal to negative t over 60 plus some constant. Now why not negative c instead of plus c? Well, c is an arbitrary constant, so it doesn't matter whether I call it a positive or a negative. It's still just some arbitrary constant. Now, to get rid of my natural logarithm, I could exponentiate both sides, and I would have the absolute value of 12,000 minus y is equal to e to the negative t over 60 plus c power. And as we mentioned in the first part of the section 4.3 material, we could rewrite this in the following way. The absolute value of 12,000 minus y is equal to e to the negative t over 60 times e to the c power. And this e raised to an arbitrary constant is just a new arbitrary constant. So since c could be any number, if I take c, or e to the c power, it's just some new arbitrary constant. Let's still call it c. So my right-hand side now becomes a constant c times e to the negative t over 60 power. And to get rid of the absolute values around my 12,000 minus y, we could take positive or negative of this quantity, c times e to the negative t over 60 power. And again, as we mentioned in the first part of the section 4.3 material, since c is arbitrary, it doesn't matter whether we have a positive or a negative out in front. When we have c as an arbitrary constant, whether it's positive or negative, it's still just an arbitrary constant. So let's just call this c for short. So we now have 12,000 minus y is equal to some constant times e to the negative t over 60 power. And then solving for y as a function of t is 12,000 minus some constant times e to the negative t over 60. So in the last part of this problem, we still have to solve for the constant c. What we have so far is just the general solution of this initial value problem. We need to find the constant c that satisfies our initial condition, which was y of 0 equals 0. So let's apply this initial condition. If we substitute 0 in for t, we have 12,000 minus c, and we are told that this value has to be 0, which implies that our constant c is 12,000, and then taking that constant and substituting back into our general solution, we have y of t is equal to 12,000 minus 12,000 times e to the negative t over 60, where again we were measuring the mass of salt in our tank in grams. So we have the following function for the amount of salt measured in grams within our tank after a period of t minutes. So once we have this function, we can answer certain related questions, say how much salt is in the tank at any specific time by plugging in that value for t, or in the next part of our problem, we're asked how much salt will be in this tank in the long run. Now, this wording, in the long run, means as time keeps increasing, as time approaches infinity, what's going to happen with the amount of salt in our tank. So let's review what we found in part B. By part B, we found the amount of salt in the tank at any given time is 12,000 minus 12,000 times e to the negative t over 60 power, measured in grams. So as time keeps increasing, as time approaches infinity, let's look at what happens with our solution. So here we're going to be taking the limit of this function, 12,000 minus 12,000 e to the negative t over 60. And the only term which depends on t is this exponential term, e to the negative t over 60, which will decay to 0 as t becomes large. So we're left with just the limit of a constant, 12,000, which is 12,000. Again, we're measuring in grams, or we might say 12 kilograms, depending on what our unit of interest is. So in the long run, eventually any fresh water that was in our tank will have flowed out of our tank, and we have a tank of 120 liters of this brine solution, which contained 100 grams per liter, hence 12,000 grams of salt within our tank, or 12 kilograms. So we can see from the problem statement that this limiting value makes sense. It's sort of what we would expect our limiting value to be based off the problem description. So in our next example, we'll consider another classic problem that makes use of separable differential equations. It is a problem involving Newton's law of cooling, which states that the temperature at which an object changes is proportional to the difference between its temperature and that of its surroundings. Now, for this particular example, we're considering a cup of coffee that has a temperature of 200 degrees when it's freshly poured, and after 1 minute, it's cooled down to a temperature of 190 in a room that's held at 70 degrees. And the question is, when will this cup of coffee reach a temperature of 150 degrees? So for this problem, what we're interested in is the temperature of a cup of coffee. So let's start by giving some notation for that quantity. We're going to let y of t be the temperature, in this example measured in degrees Fahrenheit, of this cup of coffee after t, which is going to be non-negative since we're talking about time, minutes. Now, we're given some information about the rate at which an object changes temperature. In particular, Newton's law of cooling says that the temperature changes at a rate proportional to the difference between its temperature and that of its surroundings. So we can say, by Newton's law of cooling, the rate at which our coffee changes its temperature, that is the derivative of the temperature of this coffee, is proportional to, so that is a constant multiple of, the difference between its temperature and that of its surroundings. So we're going to look at a difference here, the difference between our temperature Y and the temperature of our surroundings, which in the problem, we were told the ambient temperature of the room is 70 degrees. And we had an initial condition that at the moment this coffee was first poured, that is at time 0, it had a temperature of 200 degrees. So what we have is an initial value problem involving a separable differential equation. So we could solve this for y, making use of a separation of variables. So in my first step, I'm going to separate the variables. Let's divide both sides by y minus 70 and multiply both sides of my differential equation by dt. Now, once I've separated my variables y and t, I can then integrate both sides. And on the left-hand side, we have the natural log of the absolute value of y minus 70 is equal to kt plus some constant c. So as we've been doing in our earlier examples, to get rid of this natural logarithm, we could exponentiate on both sides. And when I exponentiate on this right-hand side, this e to the c term, we've said we could rewrite as a new constant, call it c, times e raised to the kt power. And the absolute value around my y minus 70, I could get rid of by making that constant a positive or negative constant. But whether we have a positive or negative constant, we could still just call it c. So we find then that y, as a function of t, is equal to 70 plus c times e to the kt power. Now, at this step, I can solve for my constant c by using the initial condition y of 0 equals 200. So let's see what this gives us. If we evaluate this function at 0, we have 70 plus c, which we know has to equal 200. Therefore, c is equal to 130, and y of t is then 70 plus 130 times e to the kt power. Now, we still have an unknown constant in this solution, the constant k, this constant of proportionality that appeared in our original differential equation. Now, to solve for that constant k, we can use the condition given in our problem statement that after 1 minute, our coffee has cooled to 190 degrees. So let's apply this condition where y at time 1, which is 70 plus 130 times e to the k, has to equal 190. So solving for k, we could first subtract 70 from both sides, giving me 130 e to the k is equal to 120, so that e to the k is 12 over 13, and k is then the natural log of 12 over 13. So once I have this constant k, I'm going to substitute it back into my solution. And we find that y of t is equal to 70 plus 130 times e raised to the k, which was natural log of 12/13 times t. So once we have this function for the temperature of our coffee at any given time, we're interested in determining when our coffee reaches a temperature of 150 degrees. So we're going to let our temperature, which was 70, plus 130, e to the natural log of 12/13 times t equal 150. And we want to solve for t now. So if I first subtract 70 from both sides, I would have 130 times e to the natural log of 12/13 times t is equal to 80. And then dividing by 130, we have e raised to the natural log of 12/13 t is equal to 8/13. So now, if I take the natural logarithm of both sides, we will be left with the natural logarithm of 12/13 times t is equal to the natural log of 8/13. So finally, solving for t, we could divide both sides by the natural log of 12/13, and we have log of 8/13 over log of 12/13, where time was being measured in minutes. Now, if we don't have the use of a calculator or some sort of software, we wouldn't know how to evaluate this expression for t, so we might leave our answer in this form. But of course, for practical problems, if we're interested in the time it takes for a cup of coffee to cool to a certain temperature, well, we wouldn't give our answer in terms of natural logarithms, but we might round to, say, the nearest minute. And in this case, t is approximately 6 minutes. So in our next example, we're going to consider the problem of exponential growth. So differential equations are often used in modeling population growth or decay over time. And the easiest example of population growth is the exponential growth model. So in this example, let's introduce some notation. We're going to let y of t denote the population size of some species at a general non-negative time. Now, the exponential growth model says we will assume that the population changes at a rate that is proportional to our population size. So that is the rate of change of population, or the derivative of our population size, is directly proportional to the population size, that it is some constant, r, which is positive, times the population size, y. And this constant r is called the growth rate for our population. And in general, we can have some initial condition. Let's say y of 0 is y naught, which is some non-negative value representing our initial or starting population. So this differential equation, the exponential growth model, is a separable differential equation. And in part A, we are asked to solve that exponential growth model. So using separation of variables, if we were to divide both sides through by y and multiply both sides by dt, we have dy over y is equal to r dt. And once we've separated the variables y and t, we can integrate on both sides, and we're left with the natural log of absolute value y is equal to rt plus some constant. So in order to solve for y explicitly, we could exponentiate on both sides, and we're left with y of t is equal to, well, when we exponentiate, as we said earlier, this e to the c power can be considered as a new constant times e to the rt. Now, we still need to solve for the constant c, making use of our initial condition, which was y of 0. So if we plug in 0 for t, we're just left with the constant c, and this is equal to y naught, our initial population. So substituting that constant back into our general solution, we find y of t is equal to y naught times e to the rt power. And this would be our general solution, or excuse me, our particular solution of the exponential growth model. So it says our population at any time t is equal to the initial population, y naught, times e raised to the rt power, where r is our growth rate. Now, in part B of this question, we're asked to determine the limiting behavior of our population as time goes on forever. And then we ask the question, does this seem realistic? So let's ask ourselves, what happens to y of t as t becomes large? So we're going to be looking at a limit of y naught times e to the rt as t gets large. Now in this problem, we were assuming that r was a positive constant, which means that this e to the rt term will increase without bound. And what we're finding is that our population size is becoming unboundedly large. The population size is approaching infinity. Now this does not seem very realistic. No matter what population we're describing, there's an upper limit for the population size. So this is one unrealistic feature of the exponential growth model, is there is no upper cap on how large our population can become. So here we might say this is not realistic because of the unbounded population size. Now, in the next section, we'll talk about one alternative to the exponential growth model, which is a little more realistic for population growth. But for now, let's look at one example that makes use of the exponential growth model. Here we are given a bacterial culture that starts with 1,000 bacteria, and after 2 hours, there are 2,500 bacteria. So here in part A, we are asked to find an expression for the population size after t hours. Now, based on the exponential growth model, we saw that our solution, or the population size at any given time, y of t, was equal to y naught, our initial population, times e to the rt power. And in this example, y naught, our initial population size, was 1,000. We were starting with 1,000 bacteria. Now, we still need to solve for the growth rate r. And in order to solve for the growth rate, we can use the information we're given about the population size after 2 hours. In particular, after 2 hours, or when t is equal to 2, our population size was 2,500. Now, if we plug in 2 for t in our solution, we have 1,000 times e to the 2r power, which is equal to 2,500, we were told. So solving for r, we could first divide through by 1,000, and we find e to the 2r is equal to 2.5. So 2r is equal to the natural log of 2.5, which implies that r is equal to the natural log of 2.5 divided by 2. So now, once we have this value for r, we can take this value and substitute it back into the expression that we had for our population size at any time. And what we find is that our population size y after t hours is 1,000 times e raised to the r, which we found to be the natural log of 2.5 over 2 times t. So this would be our expression for the population size after t hours. Now, once we have this expression, in part B, we are asked to find the population size after 6 hours. So in order to do that, we would let t equal to 6. And we find that our population size at times 6 is equal to 1,000 times e to the natural log of 2.5 all over 2 times t, which is 6. So we're left with 1,000 times e to the 3 times natural log of 2.5. That 3 coming from the fact that we have 6 divided by 2 in our exponent. Now, again, without the use of a calculator, it might be a little tricky to evaluate this expression. In this example, this quantity works out to 15,625. Or if we didn't have the use of a calculator, we would have to leave our answer in terms of this exponential form. Now, another question of interest for these exponential growth models is the question of how long it would take the population to reach a certain size, say 5,000. Now, in part A, we found an expression for the population at any given time, y of t. So we're going to take that general population size, 1,000 times e to the natural log of 2.5 over 2 times t, and set it equal to the desired population size, 5,000. And now to solve for t, we could start by dividing both sides by 1,000, and we have e to the natural log of 2.5 over 2 times t is equal to 5. Taking the natural logarithm of both sides, we find the natural log of 2.5 over 2 times t is equal to log 5. And so solving for t, we would first multiply both sides through by 2. So we have 2 natural log of 5. And then we're dividing by the natural log of 2.5, where time is being measured in hours. So again, without the use of a calculator, we would have to use this expression in terms of the natural logarithm for time, or if we have the use of a calculator, we could approximate this, say, to the nearest hour or tenth of an hour, whatever accuracy we need. Now, the next problem that we'll consider is very similar to exponential growth. It is the exponential decay model, which is most frequently used to model the decay of some radioactive substance over time. So in this next example, we will let y of t denote the mass of some radioactive substance at a given time t. And the exponential decay model makes the assumption that our mass will change at a rate which is proportional to the amount of material present. So that is the rate of change of mass, or the derivative of mass, dy dt, is some constant, negative k, times the mass y, where k is a positive constant called the decay rate of our substance, and we have an initial condition y of 0 equals y naught, which is representing our initial mass, how much material we started with at time 0. So in part A of this example, we are asked to solve the exponential decay model, and we can see that this is a separable differential equation. So separating our variables, we would have dy over y is equal to negative k times dt. And once I've separated my variables, y and t, I can integrate on both sides of this equation, and I find the natural log of y is equal to negative kt plus some constant. So solving for y by exponentiating, we have c times e to the negative kt power. Again, the constant c out in front is coming from the fact that we're exponentiating the constant c, which is just a new constant. Now, we still need to solve for c, making use of our initial condition, which was y of 0 is equal to y naught. Now, plugging in 0 for t, we're just left with the constant c, and we're told that has to equal our initial mass. So we find then that y of t is equal to our constant, y naught, times e to the negative kt. So much like the exponential growth model, the exponential decay model has a solution that's given by our initial mass, y naught, times e to the negative kt. So the difference here in exponential growth versus exponential decay is that our exponent is now negative, e to the negative kt. So in part B, we are asked to determine the limiting behavior of our sample as time approaches infinity. So again, as time t becomes infinitely large, we're going to look at the limit of our function as t approaches infinity. And here our function was y naught times e to the negative kt. Since k is a positive constant, e to the negative kt is describing an exponential decrease or exponential decay, and this exponential function will tend to 0. So as time increases, our mass of this sample will decay to nothing. We get a mass which, or a radioactive material which is slowly decaying to 0 mass. So in our last example, we're going to look at an application of the exponential decay model in computing, how long it will take for a sample of some particular radioactive substance to decay to a certain amount. So in this problem, we're considering half the radioactive substance carbon-14, or C14 for short, and we're given the half-life of this substance is 5,730 years. And we have a sample of carbon-14 with an initial mass of 20 micrograms. And in part A, we're asked to find a formula for the mass of carbon-14 which will remain after T years. So in our previous example, we found that using the exponential decay model, our mass of this radioactive substance at any time is given by y0 times e to the negative kt, where y0 was the initial mass. In this example, our initial mass was 20 micrograms, so we will have 20 times e to the negative kt micrograms. So we still need to solve for the constant k, our decay rate, and in order to do this, we can make use of what information we're given about the half-life. So here we were told that the half-life of this substance is 5,730 years, which means that at that time, or after 5,730 years, we will be left with half of what we started with, or 10 micrograms. So using that condition, let's see what we have for K. Y of 5730 is given by 20 times e to the negative 5730k, which we know has to equal 10. So to solve for k, we could divide both sides by 20, and we find e to the negative 5730k is equal to 1/2. So taking the natural log of both sides, we have negative 5730k is equal to the natural log of 1/2. So we find then that negative k is equal to the natural log of 1/2 over 5730. Now, once we have this expression for negative k, we can take it and substitute it into the expression that we had for y of t earlier in this example. And we find that y of t is equal to 20 times e to the negative k, which we found as natural log of 1/2 over 5730 times t, where we're measuring in micrograms. So this would be our function for the mass of carbon-14 which remains after t years. Now, once we have this, in part B of this example, we can ask for the mass remaining after a certain period of time has passed. In this case, after 1,000 years. So to find our mass, we're going to let t equal to 1,000, and we have 20 times e to the natural log of 1/2 over 5730 times 1,000 micrograms. And again, without the use of a calculator, well, this is a little tricky to evaluate. We would have to leave our answer in this form, or for practical purposes, we might approximate this. And in this case, it works out to 17.72 micrograms. Now, in the last part of this example, we are asked when will our mass be reduced to 15 micrograms. So to find that, we're going to take the expression that we found for mass in part A, 20 times e to the natural log of 1/2 over 5730 times t and set it equal to 15. Now to solve for t, we could first divide both sides through by 20, and we have e to the natural log of 1/2 over 5730 times t is equal to 15 over 20, or 3/4. Now taking the natural log of both sides, we have log of 1/2 over 5730 times t is equal to the natural log of 3/4. And so, finally, solving for t, we would multiply through by 5730 and then divide by the natural log of 1/2. And this works out to be approximately 2,378. And again, time here is being measured in years. So in this lecture, we've seen several different examples of how separable equations could be used to model some physical process, say exponential growth or decay, the rate at which an object is cooling, or the rate at which we're mixing some brine solution or some salt solution